Hi folks, Dave here. Is it really bad to run my gear on a square wave inverter? And besides, I've done it before and nothing bad happened. I will present the facts plus some highly technical information in a way that is accessible to the average DIYer. I've known for years that square wave inverters can and do damage certain appliances. In fact, it's common knowledge in some industries. But because of the complexity of the topic, you can't explain it in a single soundbite, and the information is usually buried with a lot of technical jargon. First, let's get some basic definitions clear, because often common words and meanings get diluted and diminished, causing a lot of misunderstanding, confusion, and false assumptions. Pure sine wave inverter. This is a marketing term intended to distinguish sine wave inverters from their square wave counterparts. In fact, it's not a pure sine wave at all, as there will always be some DC component, regulation artifact, or switching noise represented on the inverter output. Often this distortion is generally referenced as percentage of total harmonic distortion, or %THD. Around 3 to 5% THD is pretty good and average for a decent inverter. The figure may vary. This distortion is just referring to the sine wave being a bit rough instead of perfectly smooth and curved. Modified sine wave inverter. There's actually no such thing. The term is used for marketing to partially obscure the fact that the inverter is not a sine wave inverter at all. A sine wave is sinusoidal, meaning it's curved. A square wave cannot, by definition, be curved. It is square, or at best, angled, but it's still not sinusoidal. A more truthful term would be square wave or modified square wave, because that's in fact what it is. The term is sometimes abbreviated as MSW for modified sine wave. By the way, square wave inverters have a ton of distortion because, well, the wave is square, which in fact is a distortion of what a sine wave should look like. The most important thing you need to understand about running an appliance on a square wave inverter is what kind of appliance you're running matters a lot. Resistance loads, like a basic electromechanical space heater or electric filament light bulb, should be no problem at all. There might be a few random exceptions, but by and large, you'll be fine. Electronic and switching loads, such as computers, switch mode power supplies, and so forth, have a big asterisk beside them, so we'll address those last. Inductive loads, big problems and lots of them. And the big problems can be addressed in two parts: damage to your appliances and the human factor. The human factor is that most folks don't understand just because it didn't fail in 24 hours on a square wave doesn't mean they aren't damaging the appliance and doesn't mean it isn't going to fail. Look up the term cumulative effect. Some damage happens over time and finally manifests itself when it's too late. And the end user probably won't even realize that the appliance could have lasted longer if they had just run it on a sine wave like it was designed for. What are inductive loads? Examples of inductive loads are standard compressors and motors in air conditioners, refrigerators, and common power tools and machines. They use alternating current, or AC, to induce a magnetic field from stator to rotor, causing the motor to rotate and drive the load. This works very well on a sine wave AC source, but not too great on square wave. That is not to say it doesn't work, it just doesn't work very well. The negative effects of square wave AC on inductive motors are many. I don't promise to cover every little aspect here, but will give you enough facts to make your own educated decisions. The first problem with running an inductive motor on a square wave inverter is the startup surge. In fact, the startup surge can be like 50% higher on a square wave than on a sine wave output. Well, that's not good. Every time that surge happens, the chances of burning out the motor or part of the appliance goes much higher. And not only that, the inverter itself is also taking that surge and therefore is at an increased risk of burning out. You might think that the surge is the biggest number you saw on the watt meter when you turned the appliance on, but in fact, no, that's not the case. There's no way a human being or a slow, cheap meter can measure that surge because it's too fast and it's too brief. But the fact is, it's there and it should be taken into account in your decisions. Although inductive motors naturally have a surge when they turn on, they still have a softer start on a pure sine wave inverter than on a square wave inverter. Square wave causes a much more violent start of the inductive motor, and that is not good or helpful at all. Square wave AC causes inductive motors to run less smoothly than on a pure sine wave. What does that mean? Well, it usually means more vibration. That in turn means more wear and tear on the bearings, and again, potentially shortened appliance life. Not only that, the RPMs, or rotational speed of the motor, will not be as consistent on a modified square wave inverter as they would on a pure sine wave inverter. An inductive motor running on a square wave inverter will get hotter because it's working much harder and consuming more current. 15 to 20% more in some cases. Obviously, this is less efficient as well. An inductive motor is never going to run as efficiently on a square wave because it wasn't designed to. Square wave inverter output is much harder on inductive motors, and it will shorten their life cycle over time. The motors tend to run hotter, less efficiently, and there's an increased risk of damage and definitely a risk of shortened life cycle. You may notice that it makes a buzzing sound or seems a bit hotter, but it's hard to quantify what's actually going on. The safe assumption is you should not use a square wave inverter on your inductive loads, especially in compressors, refrigerators, air conditioners, unless you absolutely have to or it's an emergency. If you run it for only a few days like that, you can probably get away with it. So what about electronic devices such as mini-split heat pumps, computers, laptops, and appliances with digital controls? Are they harmed by square wave or modified square wave inverters? Well, you already know how square wave affects the inductive motors in some appliances, but it is a fact that square wave inverters can sometimes damage electronics too, and there's plenty of evidence for it. In fact, it's posted all over the internet if you care to do some research. Let's break this issue down into parts so it's easier to understand. The smarts inside electronic devices come from millions of semiconductor junctions. Basically, they are the brains of the system. It is true that they can be rather sensitive to noise and unstable power. These semiconductor junctions run on direct current, or DC, not alternating current, or AC. So in today's appliances, it's almost never going to be the case that you don't find some kind of power supply circuit inside. But the most common appliance circuitry that will see the square wave output first is called a switch mode power supply, or SMPS for short. You might know it as a wall wart or a power brick. SMPS circuits are found everywhere. They're in mini-split air conditioners, refrigerators, televisions, laptops, computers, dishwashers. But an SMPS doesn't only use AC. It actually runs on high voltage pulsed DC. So what's the problem? In a simple SMPS, the AC gets turned into DC by what is called a rectifier. It's basically a set of diodes that reroute the alternating current into a single direction, which creates a DC voltage. But square wave inverters can induce noise, frequencies, and harmonics into the circuitry that are not necessarily anticipated or handled properly in the design. While some SMPS circuits will handle square wave seemingly fine, others in fact don't, and there is no way to tell which one it is just by looking at it. For example, I have seen cases where a particular laptop power brick quickly overheated and burned up on a square wave inverter. Meanwhile, other power bricks work just fine. Some have different filtering and correction circuits, or circuitry that might be more sensitive to the rough AC waveform than others. So instead of becoming an electronics tech, look for these warning signs. Overheating, the appliance or power supply circuit is getting too hot, and/or you smell something burning. Just unplug it, the risk is not worth it. Hopefully no damage is done. Instability. For example, if you have a computer that suddenly starts rebooting or crashing on square wave power, but it has no problem on sine wave power, well, there's your answer. Maybe try a different power supply or just move to a sine wave inverter. Loud buzzing sounds. This is a tough one. Square wave is far more likely to induce harmful noise into circuits. We already know it affects induction motors, and buzzing is one of those symptoms. But that can also happen in electronic circuits. While some appliances might survive this, more sensitive ones could be affected. Use your best judgment. Ask yourself, is it truly wise to operate a computer, heat pump, or other expensive appliance on a square wave inverter when it makes a very loud buzzing noise? Of course not. You don't have a full understanding of electronics and circuitry, and there's potential risk involved. And then there's logic. First, if your appliance costs $3,000, why not ask the manufacturer for support? Ask them, can their appliance handle square wave AC inverter output or not? And the answer might even be in the instruction manual, so try checking that. Second, if the appliance was expensive, why not spend an extra $100 on a sine wave inverter to give it cleaner power? That square wave inverter is still useful for running less sensitive appliances or resistance loads. There's no need to abandon it. By the way, I keep a separate small sine wave inverter around specifically to run sensitive loads like computers or lab equipment. If you watched this far, you can see how the answer to this question can be complex and not always clear-cut. But it can be said, if the SMPS power supply in your appliance doesn't get hot, doesn't make loud buzzing noises, and the appliance runs absolutely perfectly, then you might be okay. Electronics are very complex, and it's not always clear to us why one circuit runs fine and another falls apart. So we have to use some logic and common sense. Folks, I hope you enjoyed this video and that it helps you out. If you don't mind, please thumbs up and like the video, and also leave a comment. That helps my work gain more exposure on this platform. Thanks for watching, and I hope to see you next time.